We are finally to the last video for our summer series of lessons. This one will cover percent yield and some new topic called combustion analysis. You could also call it stoichiometry part 2. First, let's talk about how much product you can produce from a reaction. Now, how much you can make is always determined by how much limiting reactant you used. And how much you could make is called the theoretical yield. However, you never get what you calculated. Like, you never get in lab what your theoretical yield says you should get. And the question is, why? Well, here are some potential reasons. You could lose some product when you're separating it from the mixture that it's contained in. There might be competing reactions going on with the reactant that you determined the amount that you could produce based off of. And based on some research, it appears that some reactions stop before they actually get to completion. Now, the amount of product you make is called the actual yield. So the amount that you physically get in lab is the actual yield versus how much you should have gotten from a calculation, which is your theoretical yield. When you compare these two amounts, we get what we call the percent yield. So when you take actual yield divided by theoretical yield and you times it by 100, you can figure out how efficient your reaction was. Did you get 100% of what you thought you would get? These problems tend to be tricky for students. Here are the hints that I have to give you. Label the numbers. Like I was showing you in the stoichiometry video, summarize what you have under each species in the chemical reaction. Remember that percent yield is always calculated for a product. You want to know how much you produced, not how much you started with. You will convert the given number they give you, or numbers, if it's a limiting reactant problem, to the product that the question is mentioning. That will be your theoretical yield. When you calculate percent yield, also remember that the units of the top and the bottom have to be identical. Grams methanol over grams methanol. They have to be identical. So here's a question. New industrial plants for acetic acid react liquid methanol with carbon monoxide in the presence of a catalyst. In an experiment, 15 grams of methanol and 10 grams of carbon monoxide were placed in a reaction vessel. 19.1 grams of acetic acid were obtained. What is the percent yield? So on the next slide, I have the balanced chemical reaction written out, and I'm just going to summarize what they gave us. They told us you had 15 grams of methanol reacting with 10 grams of carbon monoxide, and you produced 19.1 grams of acetic acid. Now, the first thing that I know immediately, because this is the product, this is my actual yield. I have no way of knowing how much they got in lab unless the problem tells me. They're telling you 19.1 grams were obtained. That's my actual yield. So when I go to calculate percent yield, I want actual over theoretical times 100. Right now I know my actual is 19.1 grams of HC2H3O2. I need to find my theoretical yield and times by 100%. I also know that the units of the top and the bottom have to be identical. So I need to find the grams of acetic acid I should have produced. And what I should have produced is going to be based off of what I started with. I also noticed that I have two amounts of two reactants. I groan in my head because I know that this is a limiting reactant problem. I have to do two grids. So start with the 15 grams of the methanol in one grid. In the other grid, start with the 10 grams of carbon monoxide, and then start converting. First things first, 15 grams of methanol, we got to get to the mole. A mole of methanol, when you total up its molar mass, is 32 grams. Now, what am I going to? Remember, you want the same units on the top as you do on the bottom. I need grams of acetic acid. So I have 1 mole of methanol for every 1 mole of acetic acid. And then for every mole of acetic acid, because I need grams, because I need the units to be identical, there are 60 grams of acetic acid. Total it out and I get 28.1 grams of acetic acid. Now I got to do it again. Carbon monoxide has a molar mass of 28 grams per mole. The mole ratio is still 1 mole of CO for every 1 mole of acetic acid. sorry, I got to go on a diagonal here, guys. Every mole of acetic acid, we already totaled it up, is 60 grams. Calculate it out, and you get 21.4 grams. Now, of those two numbers, think back to limiting reactant problems. What is the correct number to plug into the theoretical yield? Well, you can make the smaller of the two numbers because this is your limiting reactant. So take the 21.4 grams, plug it into your equation, and solve. I got 3 sig figs in the 19.1, 3 sig figs in the 21.4, and the 100 doesn't count. It's a part of the formula. It's not measured. And you get 89.3% yield. And in the world of chemistry, that's a pretty darn good yield. Here's another question, and these are the ones students really struggle with. Dinitrogen monoxide, commonly known as a laughing gas, can be obtained by cautiously warming ammonium nitrate according to the following equation. If the reaction has a 75% yield, so you only got 75% of what you thought, you would get what mass of ammonium nitrate must be used to produce 685 milligrams of dinitrogen monoxide. So on the next slide, I'm going to summarize what we have. Okay, according to the problem, I want to know how many grams of ammonium nitrate I have to produce 685 milligrams of dinitrogen monoxide. I also know that I have a 75% yield. Now, when I just label these things, something becomes apparent to me. This is for the product. This is the actual yield. I have to get 685 milligrams when I run this. I can't only have 75% of that 685. So that 685 goes on the top. That's milligrams of N2O. I need to figure out how many milligrams of N2O were theoretically produced to give me 75% yield. Solve for x, 75.75, because you got to divide by 100, times x equals 685. If you divide by 0.75, x is equal to 913. And remember, since the units are the same, this is milligrams of N2O, not grams of NH4NO3 like the question wants. Most times when I ask students to do this problem, they stop prematurely, not realizing or watching their units. So starting with the 913 milligrams of N2O, I now know that I need to get back to grams of ammonium nitrate. First, milligrams, there are 1,000 milligrams per 1 gram of N2O. Then molar mass, N2O is 44 grams per every mole. Every mole of N2O is equivalent to a mole of NH4NO3. I'm out of room, going to come down here. And then every mole of NH4NO3 is equal to 80 grams. Calculate it out, and I get 1.66 grams of ammonium nitrate. And I'm done. Okay, so now you've seen a percent yield problem forwards, meaning you're calculating the percent yield, and backwards, meaning it was given to you. Make sure you know how to do both types of problems. The last topic of your summer lessons is combustion analysis. And no matter who you had, the chances of you covering this topic are slim. This should probably be new for most of you. Now, remember, when you see a problem like this, it's nothing more than a complicated empirical molecular formula problem. And it will always involve combustion, which I told you is to react with oxygen. So we're going to look at a general combustion equation here so we can talk about some things. When you are trying to do a combustion analysis problem, the point is to figure out the formula of this thing here, the CXHYOZ. We want to know how many C's, how many Y's, how many O's, how many carbons, hydrogens, and oxygens there are. So when you look at this, notice, remember conservation of mass. So when you start this reaction, all the carbon that you start with ends up in the carbon dioxide. That's important. Also notice that all the hydrogen you start with ends up in the water. The problem is the oxygen. Some of the oxygen is from our hydrocarbon, some of it is from the oxygen we burned with, and no matter what, it gets split between the carbon dioxide and the water. So we got to find a way to figure out how much oxygen we have as well. you're going to work backwards. The first step is to use the grams of the carbon dioxide to figure out how many grams of carbon there were, because we know it was all conserved into carbon dioxide when it burned. You're going to use the grams of water to figure out how many grams of hydrogen there were in the compound. Then you're going to figure out, okay, if I burn 10 grams of the compound, and I know how much was carbon and I know how much was hydrogen, then you can figure out how much grams of oxygen there are by subtracting. Then you're going to do a normal empirical formula problem. You now have the grams of everything, so convert grams to moles, divide by the smallest, and yada yada yada. So here's an example question. You perform a combustion analysis on a 255 milligram sample of a substance that contains only carbon, hydrogen, and oxygen, and you find that 561 milligrams of carbon dioxide is produced, along with 306 milligrams of water. If the substance contains only carbon, hydrogen, and oxygen, what is the empirical formula? And then secondly, if the molar mass is 180, what is the molecular formula? So we're going to do A first, okay? Like I said, we're going to work backwards. We know, first off, that you got 561 milligrams of carbon dioxide. We also know you have 306 milligrams of water. So here's what you do. Start with the 561 milligrams of carbon dioxide. Let's get out of milligram land again. 1,000 to 1. And then let's get to the mole. Mass of carbon dioxide is 44 grams for every mole. Now, I can't do a mole ratio in terms of the traditional mole ratio because I can't balance it because I don't know how many carbons, hydrogens, and oxygens there are in the hydrocarbon. But what you can say is that in 1 mole of carbon dioxide, just by looking at it, how many C's do you see? 1. There's 1 mole of C. And in 1 mole of C, what's the mass? 12 grams. Total it out and you get 0.153 grams of C, or you could say it was 153 milligrams. Secondly, start with the water, 306 milligrams of water. 1,000 milligrams every gram. 18 is the mass of water for every 1 mole of water. For every mole of water, you get 2 moles of hydrogen. And I know that because when you look at water, there are 2 moles of water. Now, this 2 right here, most missed part of this problem, and it causes many students, I shouldn't say all, to get it wrong. Every mole of hydrogen is 1 gram. Calculate it out, and you get 0.034 grams of hydrogen, or you could say 34 milligrams. Okay, I'm going to go to the next slide for space. Now, I know, according to the problem, that I had 255 milligrams total of my sample. I now know that I had 153 milligrams of carbon and 34 milligrams of hydrogen. Add them up and then subtract, and I know by default that I had 68 milligrams of oxygen. Now I'm good to go. Like a typical empirical formula problem, I have 0.153 grams of carbon. I have 0.034 grams of hydrogen. And I have 0.068 grams of oxygen. Convert them all to moles. A gram of carbon for every mole of carbon. A gram of hydrogen for every mole of hydrogen. And 16 grams of oxygen for every mole of oxygen. Calculate them out and I get 0.01275 moles of carbon, 0.034 moles of hydrogen, and 0.00425 moles of oxygen. Make sure you carefully look at which one's the smallest. The smallest happens to be the last one, so we'll divide them all by 0.00425. Solve, okay, hoping for whole numbers here, and I get 381. Now, that tells me my empirical formula. That would be my answer to part A of the original question. So part A, My empirical formula is C3H8O. But I'm not done. Now let's do B. Total up the molar mass of C3H8O. 36 for the carbons, 8 for the hydrogens, 16 for the oxygen, and I get 60 grams per mole. The problem told me the molecular has a mass of 180. 180 divided by 60, and I know that my molecular formula is 3 times the size of my empirical formula. Multiply the subscripts by 3, and you end up with C9H24O3. Make sure you know how to do all these problems, and then finish the Edmodo quiz. See you in school.